Somewhere in a small patch of dark sky, astronomers found a shape that should not be easy for the universe to make. Not a planet, not a star, not a bright object floating alone in space. A pattern, a vast arrangement of galaxies so large that light itself would need more than 1 billion years to cross it from side to side. And the strange part is not only its size. The strange part is what it asks. Because for a long time, modern cosmology has depended on one quiet idea. If you zoom out far enough, the universe should become smooth. The mess should average out. The lumps should disappear into a greater order. No region should be too special. No direction should matter too much. But then the sky began to show shapes that do not sit comfortably inside that rule. A ring, an arc, an early universe that looks busier than expected, and a set of measurements that keep refusing to fall perfectly into place. This is not a story about science collapsing. It is a story about science becoming uncomfortable. It is about the moment when a dark patch of sky stops looking empty and starts looking like a question. If you enjoy calm, long-form documentaries about space, science, and the mysteries hidden inside real evidence, subscribe to The Last Signal on YouTube. Then stay with this question. Because the deepest problem may not be what astronomers found. It may be what the universe was supposed to be. The cosmological principle is the quiet rule beneath almost every modern picture of the cosmos. It does not sound dramatic at first. It does not look like a telescope image, a black hole, or a galaxy glowing at the edge of darkness. It is an assumption. But without it, the universe becomes almost impossible to calculate. Up close, space is not smooth at all. It is crowded with stars, galaxies, clusters, streams of gas, dark regions, and bright knots of matter. Gravity has spent billions of years pulling material together, gathering it into islands, threads, and crowded regions where galaxies collect like dust in the corners of a room. From inside one galaxy, the cosmos looks deeply uneven. There are stars nearby and empty darkness beyond them. There are neighboring galaxies in some directions and enormous gaps in others. There are dense clusters where hundreds or thousands of galaxies gather, and there are regions so sparse that almost nothing shines there at all. Modern cosmology allows all of that. The rule does not say that every place must look identical when viewed closely. A painted wall can look rough if your face is almost touching it. You may see scratches, bumps, grains, cracks, and tiny changes in color. From across the room, though, those details begin to vanish. The wall becomes a single surface. The cosmological principle makes a similar claim about space. It says that if the view becomes wide enough, the lumps should stop mattering. Not because they disappear, but because they average out. At the greatest scales, no direction should be truly special. No region should be the center of a privileged pattern. No side of the sky should carry a hidden structure that the opposite side does not. This idea has two parts. The first is isotropy. Isotropy means that the cosmos should look statistically the same in every direction, once the view is large enough. If a deep survey looks north, south, east, or west across unimaginable distances, the broad pattern should not prefer one direction over another. The second part is homogeneity. Homogeneity means that the cosmos should look statistically similar from place to place. A civilization far beyond the Milky Way, looking across the same enormous scale, should not find a universe built around them any more than we find one built around us. Together, these ideas remove the special observer. They tell cosmologists that our location is not the key to the whole design. We are not sitting in the middle of a cosmic arrangement made for our view. We are one point inside a much larger pattern. That may sound like a philosophical statement, but it is also a mathematical tool. If the universe becomes even enough at large scales, researchers can describe it with broad equations. They can estimate its age, its expansion, its matter content, and its possible long-term future. They can turn the sky from a collection of separate objects into a measurable whole. Without that statistical evenness, every calculation becomes local. One region might expand differently from another. One direction might carry more matter than another. The history of everything would depend too heavily on where the observer happened to stand. The cosmos would stop being a single system and become a patchwork of special cases. Now pull the view outward. Far beyond Earth, beyond the Sun, beyond the Milky Way, the familiar shapes begin to lose their edges. Galaxies become points. Clusters become faint concentrations. Vast empty regions become less like wholes and more like part of a larger texture. From that impossible distance, the bright and dark parts should blend into a fine cosmic mist. Not perfectly, not in every small region, but broadly enough that the universe can be treated as fair, balanced, and statistically readable. This is why scale matters so much. A structure thousands of light years wide is not a threat to the rule. A structure millions of light years wide is still part of ordinary cosmic architecture. Even large galaxy clusters and long filaments can fit inside the expected roughness of space. The trouble begins when organization seems to survive across distances around 1 billion light years, or even a little above that. At that point, the question changes. It is no longer only whether something is large. It is whether the cosmos is still supposed to be lumpy at that size. A giant structure at that scale touches the foundation beneath the calculation. It asks whether the wide view has really become even, or whether the pattern continues farther than the model expects. That is why an oversized arc, wall, or ring matters. It is not just another object in deep space. It is a test of the assumption that makes deep space readable at all. The cosmic web is the vast structure that gives the universe its hidden architecture. From Earth, the night sky can make space feel almost random. A star appears here, another there, a galaxy glows in one direction, and a deeper darkness opens somewhere else. It can seem as if matter was scattered loosely across the void. That picture is wrong. On the largest maps, galaxies do not sit in space like isolated sparks thrown into emptiness. They gather into long filaments, dense knots, thin sheets, and enormous hollow regions where very few galaxies shine. The universe has texture. It has corridors of matter and rooms of absence. It has places where gravity has pulled billions of stars into crowded intersections, and places where expansion has left behind almost nothing at all. This structure is called the cosmic web. The name is useful, but it can also mislead. It is not a literal net stretched through space. It is not a solid framework holding galaxies in place. It is the visible pattern left by gravity acting over cosmic time. At the center of that pattern is dark matter. Dark matter does not shine. It does not glow, burn, reflect, or announce itself through ordinary light. A telescope cannot simply look at it the way it looks at a star. Researchers know it is there because its gravity leaves marks on everything around it. It bends light. It shapes the motion of galaxies. It helps explain why clusters hold together more strongly than visible matter alone would allow. And at cosmic scales, it acts like the underlying scaffold on which ordinary matter gathers. Gas falls into the gravitational pull of dark matter. Galaxies form along those deeper lines of attraction. Clusters grow where those lines meet. The visible universe becomes a set of glowing signs placed along an unseen road system. A city at night can work the same way. From far above, the lights do not show the asphalt itself. They show where people have built along it. They reveal highways, neighborhoods, bridges, and centers of activity without making the ground directly visible. Galaxies do something similar. They trace a darker structure beneath them. They show where gravity has been strongest, where matter has gathered, and where the universe has spent billions of years building its brightest regions. Between those bright regions are voids. A void is not empty in the absolute sense. There may still be thin gas, faint galaxies, and traces of matter inside it. Yet compared with the dense walls and filaments around it, a void is almost abandoned. If a listener could drift through one of these regions, the sky would feel strangely bare. The familiar richness of the night would be gone. The nearest major galaxies might sit so far away that even their combined light would feel remote and fragile. Directions that should glitter with distant structures would instead open into a dim, patient blackness. The silence would not be dramatic. It would be spatial. It would come from the simple fact that matter had chosen other places to gather. These voids are not flaws in the cosmic picture. They are part of it. The cosmic web needs emptiness as much as it needs filaments. Without voids, the web would have no contrast. Without sparse regions, the dense regions would not stand out. The modern model of cosmology expects galaxies to form this way. Gravity does not spread matter evenly. It amplifies small differences. A region with slightly more matter pulls in more material. That added material strengthens the pull. Over immense stretches of time, small irregularities become galaxies, clusters, and the bright walls that surround deep voids. So the existence of filaments is not the problem. The existence of clusters is not the problem. The existence of empty regions is not the problem. These things are supposed to be there. They are the ordinary result of gravity doing what gravity does. The difficulty begins only when structure seems to remain organized across distances so large that the averaging effect should already have taken over. A filament can be expected. A cluster can be expected. A wall can be expected, up to a point. At some scale, though, the universe is supposed to stop behaving like a collection of connected features and begin behaving like a statistically even whole. That boundary is not a physical fence. No glowing line in space marks where acceptable structure ends. It is a theoretical limit, built from observation, probability, and the amount of time the universe has had to organize matter. Gravity works slowly across great distances. It cannot instantly coordinate galaxies separated by stretches of space so wide that light itself needs vast ages to cross them. This is why the size of a structure matters as much as its shape. A long chain of galaxies may look impressive and still fit the model. A broad region of emptiness may feel unsettling and still be expected. A giant pattern that remains coherent around 1 billion light-years, or even beyond that, is different. It begins to ask whether the web has extended farther than it should. And when that happens, the cosmic web stops being the explanation and becomes part of the question. The James Webb Space Telescope made the young universe look more crowded than many researchers expected. It did not do this with noise. It did not do it by producing one dramatic image that settled the question in a single glance. It did it more quietly. It gathered ancient light, measured it carefully, and showed astronomers objects that seemed too developed for the early cosmic dawn. The telescope was built to see infrared light. That matters because the deepest objects in space are not only far away, they are also stretched by the expansion of the cosmos. Light that began as shorter, hotter radiation has been pulled across billions of years until it arrives in longer wavelengths. Ordinary human eyes cannot see those wavelengths. Many older telescopes could only reach part of that hidden signal. James Webb was designed to catch more of it. In that sense, it does not simply look farther. It listens to light after the universe has changed its voice. Distance in astronomy is never only distance. It is also time. When a telescope receives light from a galaxy billions of light years away, it sees that galaxy as it was when the light first left. The farther the object, the younger the version of the cosmos being observed. A deep image is therefore not a normal photograph. It is more like an old message that took nearly the age of the universe to arrive. The paper has yellowed, the ink has faded, but the information inside it may still be readable. In the first years of the James Webb era, some of those messages seemed startling. Astronomers found candidate galaxies from the first several 100 million years of cosmic history. That alone was expected. The early universe was supposed to make galaxies. The surprise was their apparent maturity. Some candidates looked bright, heavy, and organized enough to raise a difficult question. How had gravity built so much so quickly? The standard picture expects structure to grow from small beginnings. Tiny irregularities in the early cosmos become slightly denser regions. Those regions pull in more matter. Over time, gas gathers, stars ignite, and galaxies assemble. That process can be powerful, but it is not instant. The first galaxies were expected to be smaller, rougher, and still forming their identities. Then James Webb found candidates that looked, at first, as if they had grown with surprising speed. One study in the journal Nature, led by Ivo Labbé and collaborators, reported 6 candidate massive galaxies from this extremely early period. One of them appeared, if confirmed, to contain a stellar mass close to that of a large modern galaxy. That possibility made the result hard to ignore. It was not just a matter of finding a faint ancient object. It was the possibility of finding something ancient that looked strangely grown up. For a moment, the beginning of the cosmos seemed less empty than expected. Picture looking at an old family photograph and seeing, in the background, a building that should not have existed yet. The picture is real. The light is real. But before rewriting the history of the street, someone has to check the date, the angle, the shadow, and the object itself. That is what astronomers had to do with these early galaxies. The first interpretation was not the final word. Some objects that looked extremely massive may have been made brighter by active black holes. A feeding, supermassive black hole can pour out energy from the center of a young galaxy. That extra light can make the galaxy seem heavier in stars than it really is. Brightness can masquerade as mass. A galaxy can look like a crowded city when part of the glow is actually coming from one furious central engine. Later work softened the most extreme crisis. The United States Space Agency, NASA, reported that some early galaxies were probably not too massive for the standard picture, once black hole light and better estimates were considered. That correction matters. It shows why science moves slowly, even when the headlines move quickly. A surprising object is measured. Then it is challenged. Then it is measured again with better tools, sharper models, and more careful assumptions. The most dramatic version of the problem became less dramatic, but it did not vanish entirely. Even after corrections, the early universe still appears efficient at making galaxies. There may be more bright young systems than many models first expected. The question shifted from a crisis to a pressure point. James Webb did not show that cosmology was broken. It showed that the first chapters of cosmic structure may have been busier, faster, and more productive than the simplest expectations allowed. That difference matters because the Big Ring is also a structure problem. So is the giant arc. So are the questions about how matter organizes itself at scales where ordinary growth should become statistically controlled. The telescope did not discover those giant patterns through the same method. It did something else. It made the early universe feel less slow. And once the young cosmos begins to look less slow, every later structure begins to carry a slightly sharper question. How much organization can the universe build before the model starts to strain? James Webb did not end the debate. It made the beginning feel crowded enough that the debate could no longer stay comfortable. Quasar absorption is the method that turned missing light into a map of the deep universe. The Big Ring was not found as a bright circle hanging in a telescope image. No single photograph showed a perfect glowing loop waiting in the dark. There was no clean outline, no rim, and no visible wall of galaxies arranged for the human eye. Instead, the discovery began with something more subtle. It began with light that had been partly removed. To understand why that matters, start with quasars. A quasar is the blazing core of a distant galaxy, powered by a supermassive black hole feeding on matter. As gas and dust fall toward that black hole, the material heats to extreme temperatures and releases enormous amounts of energy. That energy can make a quasar brighter than the entire galaxy around it. Some quasars are so luminous that their light can cross vast stretches of the cosmos and still reach our instruments. They become background lamps. They sit far behind the regions astronomers want to study, and because they are so bright, their light carries information about everything it passed through on the way to Earth. That light does not arrive untouched. As it moves across space, it passes through gas, galaxies, and faint matter that may be too dim to see directly. Some of that intervening material absorbs specific parts of the light. It removes narrow pieces from the signal. When scientists spread the arriving light into a spectrum, those missing pieces appear as dark marks. A spectrum is not a picture in the ordinary sense. It is a way of separating light into its different wavelengths, like taking a chord and hearing each note inside it. If one note is missing, something along the path took it away. That absence can reveal what the light encountered. Magnesium absorption is one of those clues. When matter containing magnesium sits between a quasar and Earth, it can remove a recognizable part of the quasar's light. Researchers can look for that mark again and again across many different quasar beams. One beam gives one narrow clue. Many beams begin to form a pattern. This is where the Sloan Digital Sky Survey becomes important. The Sloan Digital Sky Survey collected enormous amounts of information about distant objects across the sky. Within that data, researchers could examine quasar spectra and search for absorption systems that marked intervening matter. Alexia Lopez and collaborators used those magnesium absorption marks to trace material that would otherwise be almost impossible to map. The method is patient. It does not hand the observer a clean image. It gives scattered signs. One line of sight contains an absorption mark. Another contains a similar mark. A third sits at nearly the same distance. Then another appears nearby in the sky. Slowly, the missing pieces begin to connect. The process is like noticing dust, only because sunlight catches it in a dark room. The dust was already there. The beam did not create it. It simply gave the eye a way to see what had been floating unnoticed. Quasar light works in a similar way. It crosses distant matter, loses certain wavelengths, and carries those losses forward as evidence. The farther lamp exposes the nearest shadow. This is why the Big Ring is not a solid object. It is not a cosmic wheel. It is not a physical band with hard edges. It is an inferred arrangement of galaxies, gas, and galaxy clusters, recognized through many measurements spread across a deep region of sky. The same kind of mapping helped reveal the giant arc. In both cases, the shapes come from patterns in data, not from a simple photograph. That makes the discoveries easier to misunderstand. A ring sounds like something visible. An arc sounds like something drawn across darkness. But in astronomy, a structure can be real without being seen as a single object. A continent can be mapped from scattered measurements. A buried ruin can be traced from soil changes before any wall is uncovered. A distant structure can be outlined by the light it removes. There is also a deeper beauty in that. The universe did not announce the Big Ring by adding brightness. It left a pattern of absence. Dark marks in quasar light became coordinates. Coordinates became a distribution. The distribution became a shape. And the shape became a question large enough to reach the foundation of cosmology. For a moment, the empty patch of sky from the beginning of the story changes character. It is no longer just darkness. It is a region crossed by beams from distant quasars, each carrying tiny scars from matter between here and there. The listener should not picture a glowing loop. The better image is quieter. Long lines of ancient light pass through the cosmos, and somewhere along those lines, matter takes a small bite from the signal. That bite survives. It reaches a telescope. It becomes data. And after enough of those small losses are gathered together, absence begins to draw a map. The giant arc and the Big Ring are the two shapes that turned a strange measurement into a deeper cosmological problem. The first warning came from the giant arc. It appeared as a long, curved arrangement of galaxies and absorbing matter across a distant region of the sky. It was not a wall with bricks. It was not a single object moving through space. It was a claimed ultra-large structure, traced from many points, spread across a scale that did not sit comfortably inside the simplest expectation of cosmic smoothness. Its length is about 3.33 billion light-years. That number is difficult to feel. A light beam crossing from one end to the other would not be making a trip across a galaxy, or a cluster, or even a normal chain of clusters. It would be crossing a distance so wide that the word structure begins to feel almost too small. The problem is not only that the arc is long. The problem is that it appears curved, coherent, and organized over a span where the universe should already be averaging itself out. A single giant feature can still be treated cautiously. It can be tested. It can be questioned. It can be compared with simulations and placed under statistical pressure. Science has room for rare things. It has room for unlikely alignments. It has room for patterns that look meaningful at first and then become less secure as data improves. Then came the Big Ring. This second structure appeared in the same broad cosmic conversation, and it carried a shape that was even harder to ignore. The Big Ring is about 1.33 billion light-years across. Its full edge is close to 4 billion light-years around. Again, it is not a solid hoop. It is not a glowing wheel suspended in the darkness. It is an arrangement inferred from galaxies, galaxy clusters, and absorption systems, recognized through their positions across deep space. But the shape matters. From Earth, the ring appears almost circular. It does not simply stretch in one direction like a long filament. It curves back on itself. It suggests a pattern with a beginning that almost meets its end. That visual impression is part of what makes it so unsettling. The cosmos can build long threads. It can build dense knots. It can surround enormous voids with matter. A ring at this scale asks for something more specific. It asks why matter would arrange itself into a loop so broad that the loop itself touches the expected limit of cosmic structure. The deeper difficulty comes from the pair. The giant arc and the big ring appear at roughly the same cosmic distance. They belong to roughly the same era of the universe. They also sit only about 12 degrees apart on the sky, about the width of a fist held out at arm's length. To a casual observer, 12 degrees sounds wide. In everyday sky watching, it is a noticeable gap. In cosmology, when the objects involved span billions of light years, that separation begins to feel like proximity. One giant feature can be a rare accident. Two nearby giants begin to look less like a coincidence and more like a region asking to be explained. Picture two faint marks found on the same sheet of glass. One mark might be dismissed as a scratch. A second mark, close to the first and shaped with the same strange confidence, changes the mood of the room. The glass may still be ordinary. The marks may still have a harmless cause. But the observer no longer looks at the surface in the same way. That is the feeling these structures create. They do not destroy the standard model by existing. They make its quiet assumptions work harder. The Big Ring also has another complication. Further analysis suggests that the shape may not be a simple flat circle. It may be more like a coil or corkscrew, aligned in such a way that we see it almost along its length. That image is stranger than a ring drawn on paper. It is closer to a vast spring in deep space, turned so that its spiral faces Earth. The shape would still be traced through data, rather than seen as a shining object. Yet the geometry matters because different shapes point toward different possible explanations. A flat circular pattern is one kind of problem. A coil-like arrangement is another. Each asks how matter could keep such a coordinated form across such an enormous distance. One possible explanation comes from baryon acoustic oscillations. These are ancient sound wave patterns from the early universe, frozen into the distribution of matter after the young cosmos cooled enough for light to move freely. They can leave a preferred scale in the way galaxies cluster. They are not fantasy. They are part of established cosmology. But the Big Ring does not fit that explanation neatly. The expected ancient sound pattern is smaller and more spherical in character than this structure appears to be. The ring is too large for an easy match. Its apparent shape also does not behave like the standard fossil shell that baryon acoustic oscillations would suggest. So the explanation is tempting, but uncomfortable. It points toward a known physical effect, then fails to cover the whole shape cleanly. That is often where the most serious scientific problems live. not in complete ignorance, not in total contradiction, but in the narrow space where a known idea almost works, then leaves something important outside its reach. The giant arc created the first pressure. The Big Ring increased it. Together they form a question with three parts. Why so large? Why so shaped? Why so near each other in the same deep region of sky? The most disturbing thing about the pair is not scale alone. It is scale with geometry. It is geometry with proximity. It is the possibility that the dark patch of sky was never empty, never ordinary, and never as statistically forgettable as it first appeared. Scientific caution is the reason the Big Ring matters without becoming a reckless claim. Before any discovery is allowed to threaten cosmology, researchers try to make it disappear in every ordinary way they can. That may sound disappointing. It may feel like the slowest possible reaction to something enormous. Yet this is exactly what gives the mystery weight. A strange shape in the sky is not enough. A surprising measurement is not enough. A pattern that looks meaningful is not enough. Science asks the colder question first. Could the pattern be a mistake? Could the method have drawn a boundary where nature placed none? Could the human eye be finishing a shape that the universe did not actually make? The first ordinary problem is definition. Large cosmic structures do not come with edges. There is no bright outline around a galaxy wall. There is no sign in space marking where an arc begins or where a ring ends. Matter fades gradually from dense regions into thinner ones. Galaxies group, stretch, scatter, and overlap in ways that depend on distance, direction, and the method used to map them. That means a structure can partly depend on how researchers define the group. Change the threshold, and the shape may grow. Change the sample, and the edge may shift. Change the statistical tool, and a pattern may become stronger or weaker. This does not make the structure fake. It means the structure must be handled with care. The universe is not a drawing with clean ink lines. It is a field of points, distances, probabilities, and missing information. The second ordinary problem is pattern recognition. The human mind is extremely good at finding shapes. That strength helped our ancestors survive. It helps a face stand out in a crowd. It helps a track stand out in mud. It helps a warning sign stand out before the danger is fully understood. In astronomy, the same instinct can become dangerous. Stars become constellations because the mind connects them. Clouds become animals because the mind completes the outline. Random marks can begin to look arranged if the observer wants arrangement badly enough. Astronomy has seen this many times. Early maps, unclear images, and limited data have often produced shapes that later became less convincing. More information can sharpen a mystery. It can also dissolve one. That is why statistics matter. Statistics are the guardrail between discovery and wishful seeing. They ask how often a random distribution might create something similar by chance. They ask whether the structure remains unusual after the search method itself is considered. They ask whether the same data could have produced many possible shapes, with one strange-looking result selected afterward. This is not a small detail. If researchers look across enough sky, across enough distances, and across enough possible groupings, rare patterns will appear somewhere. A rare-looking arrangement is not automatically meaningful unless the odds remain unusual, after all that searching is taken into account. This is one reason some scientists remain cautious about the Big Ring and the giant arc. They do not need to deny that the data is interesting. They only need to ask whether the interpretation is strong enough They ask whether the boundaries are stable. They ask whether the pattern survives different tests. They ask whether simulations of a universe that still obeys the cosmological principle can produce features that look somewhat similar. That last point matters. Recent simulation work has suggested that very large arc-like arrangements may appear even inside models, where the universe remains statistically even at the greatest scales. If that is true, a large arc alone may not be enough to overturn the rule. It may be rare, it may be surprising. It may still fit inside a universe that becomes smooth when viewed properly. This is the skeptical case at its strongest. It says that the cosmos is allowed to contain unlikely shapes. It says that large-scale structure is messy to define. It says that an apparent violation of smoothness must survive every possible attempt to explain it through chance, mapping, selection, and simulation. That position is not cowardice. It is discipline. The difficult part is that caution does not erase the problem either. The Big Ring and the giant arc are not ordinary small features being exaggerated for drama. They are large, oddly shaped, and close enough in cosmic terms to make researchers look again. Their scale presses against the expected limit. Their geometry is not easy to place inside the simplest explanations. Their shared region of sky makes them harder to dismiss as isolated curiosities. So the honest position sits between two temptations. One temptation is to say the model has already failed. The other is to say nothing important is happening. Neither answer is careful enough. A listener can picture the problem like a faint track in snow at the edge of a forest. From a distance, it looks deliberate. Up close, wind may have softened it, branches may have crossed it, and shadows may have made it seem clearer than it is. The track might belong to something real. It might also be a trick of weather and angle. The only honest response is to keep looking until the shape either sharpens or fades. That is where the Big Ring stands. It survives because the simple explanations have not fully settled it. It remains under pressure because the extraordinary explanations have not earned victory. The mystery is stronger when the boring explanations come first. Not because they make the discovery smaller, because after they have done their work, whatever remains becomes harder to ignore. Other cracks in the same wall appear when the Big Ring is placed beside the wider problems of modern cosmology. The ring is not alone in making researchers pause. The giant arc is already part of its immediate neighborhood. But beyond those two structures, other measurements have also created a feeling that the universe is slightly less obedient than the cleanest model would prefer. None of these problems proves that the standard picture is wrong. None of them automatically shares the same cause. They may be separate issues. Some may fade as instruments improve. Some may turn out to be ordinary measurement problems wearing unusual shapes. But together, they explain why cosmologists keep testing the foundation so intensely. One of the oldest and most important pieces of evidence is the cosmic microwave background. This is the cooled afterglow of the early universe. It is ancient light, stretched and weakened until it fills the whole sky as a faint radiation, left from a time when the cosmos was hot, dense, and almost opaque. It matters because it gives researchers a map of the universe when structure was still young. Long before galaxies formed into the shapes seen today, tiny differences in temperature and density were already present. Those tiny differences became the starting conditions for everything that followed. In the standard picture, the cosmic microwave background should be statistically even across the sky. not perfectly blank, not absolutely identical in every direction, but even enough that no huge direction in space should seem strangely preferred. Most of the map behaves with remarkable discipline. That is why it became one of cosmology's strongest supports. Yet some large-scale patterns in that ancient glow have raised questions. One of the most discussed is an unusual alignment, sometimes called the axis of evil. The nickname is dramatic, but the issue behind it is technical. Some of the largest patterns in the cosmic microwave background appear more aligned than researchers first expected. For some scientists, that alignment is an interesting anomaly. For others, it may be a statistical accident, an effect of how the data is handled, or a feature that becomes less troubling when examined with enough caution. The point is not that the ancient light has betrayed the model. The point is that even one of the model's strongest pillars contains details that still invite argument. Pause for a moment on what that means. The entire sky carries a weak glow from the early universe. It is everywhere, and almost nowhere at once. It is not a star, not a galaxy, and not a visible surface. It is a low, cold memory of a hotter beginning, arriving from every direction with tiny variations written into it. To map it is to read the universe before it had built almost anything recognizable. And in that nearly featureless light, a few broad patterns still make researchers uneasy. Another pressure point is the Hubble tension. This is not a disagreement about whether the universe expands. It does. The problem is that two trusted ways of measuring that expansion do not fully agree. One method looks back to the early universe and uses the cosmic microwave background to infer how fast space should be expanding today. Another method measures the nearby universe more directly, using objects whose distances and brightness can be compared. The answers come close, but not close enough. The difference has survived long enough that it cannot be brushed aside casually. It is like two reliable clocks in the same observatory, both maintained carefully, both respected, both refusing to show exactly the same time. Maybe one clock has a hidden flaw. Maybe the room itself is affecting them in a way no one has fully accounted for. Or maybe the disagreement is pointing towards something deeper in the machinery of the cosmos. Researchers do not know yet. That uncertainty is what gives the tension its force. Then there is dark energy. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. The phrase sounds like an answer, but it is closer to a label placed on an unknown. In the simplest version of the standard model, dark energy behaves like a constant property of space. It does not change with time. It does not grow more complicated as the universe ages. It simply keeps pushing the expansion in a way the equations can describe. Recently, data from the Dark Energy Spectroscopic Instrument has added another careful question. When combined with other measurements, the instrument's results have strengthened hints that dark energy may change over time. That would be serious if confirmed. It would mean the force behind cosmic acceleration is not as simple as the cleanest version of the model assumes. But the evidence has not reached the usual discovery threshold. The correct word is hint, not conclusion. The correct mood is attention, not panic. This is the pattern across all these problems. The big ring strains the expectation of large-scale smoothness. The giant arc adds another oversized structure nearby. The cosmic microwave background contains broad alignments that remain debated. The Hubble tension keeps two expansion measurements from settling into agreement. Dark energy may be less constant than the simplest picture says. Each issue has its own evidence. Each issue has its own skeptics. Each issue may have its own ordinary explanation. They do not need to be forced into one grand answer. That would be too easy. It would turn science into storytelling before the measurements had earned it. The more careful view is also more interesting. Modern cosmology works astonishingly well across most of what it tries to explain. It explains the expansion of space, the growth of galaxies, the relic glow of the early universe, and the broad distribution of matter with extraordinary success. That success is exactly why the remaining tensions matter. A weak model can fail anywhere. A strong model becomes interesting when it fails only in certain stubborn places. The standard picture is not collapsing. It is being pressed at its edges. And the cracks are difficult to ignore precisely because the wall still stands. Cosmic strings and cyclic cosmology belong to the edge of the question, where ordinary explanations no longer feel fully satisfying. This is the place where the subject can easily be misunderstood. When scientists face a difficult structure, they do not need to leap into fantasy. They do not need to abandon caution. They do not need to claim that every strange pattern is a message from some hidden design. The better response is narrower and more disciplined. If familiar explanations fail to settle the matter, researchers test whether serious but unconfirmed ideas could describe what the data seems to show. That does not make those ideas true. It only means the question has reached a depth where established tools may not feel complete. One of those ideas is the cosmic string. A cosmic string is a hypothetical defect from the earliest moments of the universe. It is not a string in the ordinary sense. It is not thread, wire, rope, or anything that could be touched. It would be more like a thin line of trapped energy left behind as the young cosmos changed state. Some theories suggest that, as the universe cooled and expanded, certain transitions could have left defects behind. A useful comparison is cooling glass. When glass cools unevenly, stress can remain locked inside it. The surface may look smooth, but hidden lines of tension can still shape how it cracks later. A cosmic string would be far stranger and far more powerful, but the basic feeling is similar. It would be an ancient mark from a time when the universe itself was changing form. If such objects exist, they could influence matter over enormous distances. Their gravity might pull on surrounding material. They might help organize galaxies along large lines or leave subtle traces in the distribution of matter. That is why they attract attention in discussions of unusual structures. They would be old enough to come from the beginning. They would be large enough to matter across cosmic scales. And they would not rely only on slow, ordinary gravitational growth after galaxies began to form. But the caution is just as important as the attraction. No cosmic string has been directly observed. No telescope has revealed one as a confirmed object. No measurement has forced cosmology to accept them as real. They remain hypothetical. They are possible ingredients in some theories, not established pieces of the cosmic inventory. That distinction has to stay clear. A possible explanation is not an answer. A mathematically serious idea is not the same as measured evidence. Another more radical idea is associated with Roger Penrose. It is called conformal cyclic cosmology, though the phrase itself can make the idea sound colder than it feels. After the first mention, it is easier to think of it as the cyclic idea. In this view, the universe may not be a single story with one absolute beginning and one final ending. Instead, one cosmic era could give way to another, with the remote future of one universe connected in a strange mathematical way to the beginning of the next. Some researchers have considered whether ring-like patterns might be connected to traces from a previous cosmic era. The idea is controversial. It is also difficult to test. That difficulty matters because a theory can become seductive when it gives a shape a deeper meaning. A ring already feels intentional to the human mind. A circle feels complete. It feels designed, even when it is only geometry. So any theory that connects circular patterns to a previous universe must be handled with unusual care. The shape cannot be allowed to make the argument by itself. Data must carry the weight. Measurements must survive criticism. The pattern must remain after chance, selection, and ordinary structure formation have been tested. Without that, the cyclic idea remains a possibility at the border of physics rather than a conclusion. There is also an even broader possibility. Perhaps the universe is not as smooth at the largest scales as the standard picture assumes. Perhaps structure continues farther upward, repeating in some rough way from smaller scales to larger ones. That would be a fractal-like universe. In such a cosmos, the idea of a final smoothing scale would weaken. Galaxies would gather into clusters, clusters into larger arrangements, and those arrangements into still larger patterns without the same clean statistical ending. This would challenge the cosmological principle deeply. It would not merely add one strange structure. It would change the expectation that the widest view eventually becomes even. But this is the most extreme reading. Most evidence still supports large-scale statistical smoothness overall. The cosmic microwave background, galaxy surveys, and the broad success of the standard model all argue against abandoning the principle too quickly. A fractal-like cosmos remains a powerful thought, not the mainstream answer. This is where the mood of the mystery changes. It is no longer only about one ring or one arc. It is about the boundary between what has been measured and what can only be carefully proposed. Picture a map that has been drawn with remarkable precision across most of the page. Galaxies, expansion, dark matter, early light, and cosmic structure all have their place. Then, near one edge, the ink begins to thin. The lines do not vanish completely. They become uncertain. The map still guides the traveler, but the blank region asks for humility. That is where cosmic strings, cyclic cosmology, and fractal-like structure sit. They are not victories over the standard model. They are not final explanations waiting to be declared. They are serious possibilities placed at the edge of a serious problem. The strangest answers are not answers yet. They are signs of how deep the question has become. Future sky surveys may decide whether the big ring is an outlier, an error, or the first visible edge of a larger pattern. The answer will probably not arrive as one dramatic image. It may not appear as a single discovery announced with a clean sentence and a finished explanation. More likely, it will come slowly. It will come through maps. It will come through millions of measured points, each one placed more carefully than before. It will come through distances, spectra, galaxy shapes, faint distortions, and repeated views of the same dark sky. This is the patient side of cosmology. The universe does not always answer by revealing one object. Sometimes it answers by letting the map become too detailed for the wrong idea to survive. The dark energy spectroscopic instrument is one of the tools building that detail. Its work is to give depth to enormous numbers of galaxies and quasars. A flat image of the sky can show where objects appear from Earth, but it cannot fully show how far away they are. Without distance, the sky is like a photograph of falling snow where every flake seems pressed onto the same glass. Some flakes may be close enough to touch. Others may be far beyond the window. Only depth turns the image into space. That is what a large spectroscopic survey can provide. It measures how light has been stretched by expansion. It places galaxies and quasars into a three-dimensional cosmic map. With enough points, researchers can see whether matter truly smooths out at the largest scales, or whether strange arrangements keep appearing beyond the expected ceiling. That question sits directly beneath the Big Ring and the giant arc. If future maps reveal many similar structures, the problem becomes harder to dismiss. If the ring begins to look like a rare alignment produced by limited data, the pressure on the standard picture may ease. Either outcome would matter. A mystery fading under better measurement is not a failure. It is one of the ways science cleans the glass. Another important instrument is Euclid. Euclid is a European space telescope built to study the dark universe by measuring galaxy shapes, distances, and the bending of light by gravity. That bending is called gravitational lensing. It happens because mass curves the path of light. A galaxy's image can be subtly stretched by matter between the galaxy and the telescope. Those distortions are tiny. They do not look like obvious smears in ordinary viewing, but across huge numbers of galaxies, they can reveal where unseen matter lies. In this way, Euclid can help map the dark structure beneath the visible one. It can trace not only where galaxies shine, but where gravity quietly gathers. That matters because the deepest questions here are not only about visible objects, they are about the distribution of matter itself. If the largest structures are real, the map of gravity must make room for them. If they are statistical accidents, better gravitational mapping should help show that too. The Vera C. Rubin Observatory adds a different kind of patience. It is designed to survey the sky repeatedly and deeply. It will not simply look once and move on. It will return again and again, building a changing record of the heavens. That repeated vision can reveal transient events, faint objects, and large patterns that only become clear when the same sky is watched over time. There is something almost quiet about that approach. No single glance is trusted too much. No single patch of darkness is accepted as empty too quickly. The sky is visited again. The record grows. The faint becomes less faint. The uncertain begins to take shape, or disappears under the weight of better evidence. The James Webb Space Telescope also remains part of this future. Its role is not mainly to map every galaxy across the whole sky. Its strength is depth. It can keep studying early galaxies, ancient light, and the young cosmic web in sharper detail. It can show whether the early universe was truly more efficient at forming galaxies than expected, or whether better interpretation continues to soften the surprise. That question connects back to the giant structures in a quiet way. If matter organized itself earlier or faster than the simplest models predicted, then later large-scale structures may need to be understood with greater care. Not because one proves the other, but because both ask how quickly order can appear in a universe ruled by gravity, expansion, dark matter, and time. The coming maps will have to separate three possibilities. The first is that the Big Ring and the giant arc are rare but acceptable outliers. In that case, they may feel strange to us while still fitting inside a universe that becomes statistically even at the greatest scales. The second is that they are artifacts of method, selection, or limited data. In that case, sharper surveys may redraw their edges until the mystery weakens. The third is the most serious. They may be part of a wider pattern that has not yet been mapped clearly enough. If that happens, the cosmological principle would not fall in a single moment. It would be questioned more slowly. Its boundaries would be tested. Its scale would be remeasured. Its meaning would have to become more precise. That is how major changes often begin, not with one clean break, but with a rule that keeps working almost everywhere, except in the places where the new map refuses to cooperate. Return now to the dark patch of sky where the story began. At first, it looked empty. Then quasar light crossed it. Absorption marks appeared. A ring emerged from missing pieces of light. An arc sat nearby. Other tensions gathered around the same larger question. Now the patch is no longer only a patch. It is a test. It is a small part of the sky where the universe may be ordinary, or may be showing the first outline of something wider than expected. The final image is not a finished answer. It is a photograph slowly developing in a dark room. At first, there is only blackness. Then pale marks begin to surface. Then edges appear. Then the viewer realizes that the picture was present from the beginning, waiting for enough light to reveal it. Cosmology is waiting in that same way, not for certainty handed down all at once, not for one ring to explain everything, but for galaxies counted one by one, distances measured one by one, and maps filled in until the universe either becomes smooth again or refuses to do so.